Good afternoon. I am presenting my research paper for 7th International Multidisciplinary Conference on Current Research Trend, IMCCRT 2023. My abstract ID is IMCCRT 2023-4027. My research paper title is Quantum Capacitance and Fermi Level Change in Graphene Nanoribbon Due to Gas Sensing. Presented by myself, Fahrin Rahman, Senior Lecturer, Department of Tripoli, European University of Bangladesh, Dhaka. My email ID is fahrinrahmaneub@gmail.com. Abstract. In my research work, I have used semi-empirical computations to examine the property of graphene nanoribbon. Graphene nanoribbon, the short form of graphene nanoribbon is GNR. We have used GNR as a gas sensor with interaction of H2O gas molecule for both pure and defective GNRs, which has been generated in Atomistix Toolkit ATK software. We have used Virtual NanoLab, which is a part of this Atomistix Toolkit ATK software. Density of states DOS diagram of GNR or graphene before and after the interaction with gas molecules were discovered to be different, which has been observed in MATLAB software. Density of states refers to the number of different states at a particular level, and in those levels, electrons are allowed to occupy. It's vital to look at the quantum capacitance when examining graphene's electrical properties. So this study looked at change in quantum capacitance and Fermi level of graphene before and after gas sensing, and the results were produced with necessary equations. Using a three-electrode electrochemical setup, we are able to directly quantify graphene's quantum capacitance as a function of gate potential. Quantum capacitance is also called chemical capacitance, which is actually refers to the variation of electrochemical potential, and in deeply we can say it is called the variation of electrical charge of a device in a particular surface. Okay. If graphene is used in a highly sensitive capacitive circuit, the change in Fermi energy was determined from the experimental data of changed density of states. Although this research has some limitations and future scopes, we can propose that the change in Fermi energy level can be approximately 9.5 electron volt with respect to the quantum capacitance of fabricated graphene interacting with H2O, which is used as a MOSFET in this work. Objective of this work. First of all, to conduct a simulation to see the effect of H2O on defect-free and with defect graphene nanoribbon. And secondly, to conduct a simulation for observing change of quantum capacitance and Fermi level after graphene sense gas molecule. Introduction. Graphenes are members of new family of nanomaterials with semiconducting or metallic characteristics that are now being studied for intriguing quantum mechanical properties which can be implied in electrical features. All varieties of graphene have a finite band gap. As a result, gas molecule absorption is projected to have a greater impact on changing the electrical characteristics of graphenes. As a result, graphene is expected to be more sensitive to gases and perform better as electrical device. The perspective of graphene as a sensor has been proven in a number of practical and theoretical analyses. Nanosensors constructed out of graphene have the ability to detect specific events, such as when a gas molecule attaches to or detaches from the material's surface. We choose armchair-edged graphene to use as a gas sensor in our simulation. After doping with impurity molecules, the GNR or graphene band gap can alter, resulting in variation in the band. After absorbing gas molecules onto the GNR surface, the band gap shifts, modulating the electrical and physical properties. Density of states. This is the part of our research elaborations. First of all, I'm explaining about density of states. Density of states is actually number of different levels or different states for a particular energy level. And in that energy level, most number of charges can occupy. First of all, we have pointed out that the value of density of states and band structure of uncharged graphene with sensing of gas molecule and without sensing of gas molecule were obtained from the simulator. Our simulator is virtual nanolab, which is the part of Atomistix Toolkit. The analysis clearly shows that the changes of DOS or density of states from the simulation of virtual nanolab adheres to anticipated structure as the Fermi level. Actually, the meaning of this is after interacting with gas molecules, interacting with gas molecules, the Fermi level will change its position. This is actually our main research focus. When it is obvious that the new values of density of states of graphene with defect fluctuate significantly after touching the gas molecules under examination, and the form of this fluctuation differs depending on the gas. We have used the temperature value 298 Kelvin, considering the Fermi level. Boltzmann constant is fixed Kb. The value of Kb is 8.617333030 into 10 inverse 2 milli-electron volt inverse Kelvin. This is the slide this is the slide, and here some equations of quantum capacitance and density of states have been stated. Quantum capacitance is actually the chemical capacitance. In this research, before and after interacting with gas molecules, the charge concentration of graphene will change. The charge concentration of graphene before interacting with gas molecules and after interacting with gas molecules will vary. And the highest number of charge which a graphene can occupy is called its capacitance or chemical capacitance, or it is also called quantum capacitance. After interacting with gas molecules, this quantum capacitance will actually change. So first of all, the equation of CQ, which is quantum capacitance, is stated as E square into del N divided by del E. The calculation of DOS is DOS square plus minus T prime square T square plus 4T square beta plus 4T square beta square plus 2T square beta kx square a square divided by 4 pi T square beta a square kx. Where kx is the wave vector in the x direction, which is calculated as E, which is the energy level of graphene. This is one of the important parameter of this research, which is the energy level of graphene. E is equal to Eg minus x into kBt. Kb is Boltzmann constant here. X is the direction. Is this the direction towards the charge move? X is the direction, and in this direction the charge will move. And Eg is the standard band gap, the standard band gap of graphene without defect. Actually, before sensing with the gas molecule, graphene has a particular band gap, which is Eg here. And T is the temperature, and the value of temperature is T. Then with normalized Fermi energy, I mean without sensing with any gas molecule, eta, this symbol is called eta. Eta is equal to EF minus EG divided by KBT. EF is the Fermi level. EF is the actual Fermi level. EG is the standard band gap. EG is the standard band gap divided by KBT. KB is the Boltzmann constant and T is the standard temperature, which is 298 Kelvin. And the value of X is also determined. X is equal to E minus EG divided by KBT. So the equation of quantum capacitance will become plus minus E square into DOS square, which is density of states, into 1 divided by 1 plus e to the power x minus n. This DOS density of states we will get from our simulation. From our simulation, we actually get two parameter here. I'm marking it with spotlight. We will observe this DOS and this E from our simulating software, Virtual Nanolab. And after using equation 6, we will observe that the more the quantum capacitance increases, the more the carrier concentration also changes. It also ultimately means the more the quantum capacitance increases, the charge occupying capacity will also increase, which will ultimately improve the electrical property of a graphene. That's our main target in our research. Okay, we are continuing from our previous slide. In terms of Fermi velocity, carrier density, temperature, and other fundamental physical parameters, the theory offers a quantitative account of graphene's quantum capacitance. This equation is when we use graphene in graphene MOSFET, we will get a top gate voltage, which is VG here. CI is the double layer capacitance. CI is the double layer capacitance of the ionic liquid. Actually, CI is the capacitance of the material which is used in graphene MOSFET, and the standard value of CI is 20 mfcm cm inverse square. And the geometric capacitance of the top gate graphene is Cg is equal to 6 femto micrometer inverse square. This is the observation slide. These two results, which are figure 2 and figure 3, we have got these two results from our simulator Virtual Nanolab. Here, the black and white molecule distribution is graphene. The black and white, I'm using spotlight. This black and white slide sheet is graphene sheet, and this red marked, this red molecule is H2O molecule. From our observation, we are watching that this graphene slide sheet is defect free. But in this figure, if we observe very closely, and I'm marking an area here, we are observing a defect of graphene. Here is a defect of graphene. So this is a defected graphene sheet with the H2O molecule. Figure 2, when GNR, the graphene, when it has no defect, and the distance of graphene and H2O molecule is around 0.25 nanometer, and in this figure, the distance of H2O and the graphene is also 0.25 nanometer, but graphene has defect. We have observed this result from Virtual Nanolab, actually. Okay, now we have put our simulated virtual nanolabs value. Now we have used virtual nanolab, and we have also generated some values when we have used defected GNR and interacting it with H2O. We have got some results, and we have put our results on MATLAB software, and after that we have got a curve, and in this curve in x-axis these values are, I'm using notation here. In x-axis, these values are energy level of graphene, and in y-axis, these values are density of states of graphene nanoribbon defect. The values of the energy level and values of density of states, which is DOS, have been generated in virtual nanolab. We just used it. From our for our simulation, we used quantum-wise version of Atomistix Toolkit ATK 13.8.2. ATK is a set of atomic scale simulators that can calculate properties of nanoscale systems. We got our result, which has been shown. This is our result for it is just a result of a graphene which is defect free. That's it. It is the next slide. And we are continuing. In our next slide, we have observed that, I'm using a notation, we have observed that in x-axis, there are some energy levels, and this figure is for a defected graphene. For a defected graphene, there are two colored curves. One is blue color. This is for graphene. This is for graphene, and the red color curve is for H2O. Before interacting with H2O, for a defected graphene, we will get this blue curve. This figure differs from the previous figure. Differs from the previous figure. The previous figure was from the previous figure and this, and the previous figure and this figure varies a lot, because in the previous figure the graphene was defect free, but in this figure the graphene is defected. So our blue curve is like that, not like our previous figure. But after interacting with H2O, we will get that red curve. Energy level and density of states of graphene which is defected and distance is 0.25 nanometer shifted left than the energy level of density of states of graphene. This has been shifted left from the blue curve. The red has been shifted left from the blue curve. Okay, now we are moving to the next slide. This is the graph which is showing the quantum capacitance of graphene. X-axis barabar, x-axis, in x-axis we have put the value of graphene energy level, and in y-axis we have put the quantum capacitance value. So for a defect-free GNR, we have got this type of curve, and the next curve, after interacting a defected GNR with H2O molecule, we will get this curve. In x-axis, graphene energy, the value of graphene energy, and in y-axis, the value of quantum capacitance. The quantum capacitance is mostly high from the range of 0 to this is approximately 0.145. In the previous curve of density of states, we have observed that between 0 and 0.1, approximately between 0 and 0.1, we have got density of states value very high. And referring to this figure, we can observe that in this figure, we are also observing in this figure, referring to the previous figure, we have got highest value in the range of 0 to 0.1. Okay, as the DOS figure. Okay, we are moving to the next slide. Now, we have just calculated our Fermi energy level after getting the result from previous slide. In figure 8 for defective GNR, the red curve shows energy level versus changed quantum capacitance. The quantum capacitance has been changed. We can observe this. This figure and the next figure are not same. Sorry. This figure and this figure are not same. So, so we can say after interacting with H2O, the quantum capacitance has been changed. The quantum capacitance of this figure and quantum capacitance of this figure is changing. Are not is not same. Okay. The change in Fermi energy for a given change in top gate voltage, or we can say for a given change in quantum capacitance, can hence be changed as we can use this formula for calculating our Fermi energy level. And now we have got 9.58 volt. Okay, for if we take the reference value 0.145 electron volt. Conclusion. In the above work, the quantum capacitance of graphene has been measured with the in previous slide the value was changed. In previous slide the value was changed. Actually, by mistake I have used negative sign, but this value will be 0.145, not minus 0.145. By mistake I have added this minus. Okay, apologies. Conclusion. In the above work, the quantum capacitance of graphene has been measured with the change value of DOS of graphene, which sensed gas. It refers to non-ideal graphene that contains an acceptor. H2 is a kind of acceptor, which can accept electron or which can share electron with graphene and give a hole to graphene. So this is an acceptor. Okay, on both sides of the minimum, the quantum capacitance increases linearly with potential, resulting in a completely different Fermi level for non-ideal defective graphene with gas sensing and doping properties. Thank you so much for watching this slide. Goodbye.